Securing CI/CD pipelines with Vault for secrets management. Welcome back to the channel, tech enthusiasts. Today, we're diving deep into a topic that's absolutely crucial for modern software development: securing your CI/CD pipelines. If you've ever found yourself hard-coding API keys, database passwords, or other sensitive credentials directly into your build scripts, environment variables in your CI/CD settings, or even worse, committing them to your source code repository, then this video is a must-watch. This common practice is a massive security vulnerability, like leaving your front door wide open with a sign saying "Valuables inside." It exposes your sensitive data to anyone who gains access to your repository or pipeline logs, making you an easy target for breaches. We've all seen the news headlines, and nobody wants to be next. Imagine the nightmare of a leaked secret compromising your entire production environment. It's not just about protecting your data, it's about protecting your reputation and your users' trust. So, how do we solve this pervasive problem effectively and securely? The answer lies in robust secrets management. That's where HashiCorp Vault comes in. Vault is a powerful, centralized secrets management tool designed to securely store, manage, and distribute sensitive data. Think of it as a highly fortified, digital bank vault for all your application and infrastructure secrets. Instead of scattering secrets across various configurations, files, or environment variables, Vault provides a single, audited source of truth. It handles the lifecycle of secrets, from generation and storage to access and revocation. It offers features like dynamic secrets, which generate credentials on demand, and detailed audit logs, giving you full visibility into who accessed what, when, and from where. This level of control and security is simply impossible to achieve with ad hoc methods, making Vault an indispensable tool for any modern, secure development pipeline. Vault's power comes from its modular architecture, specifically its secrets engines and authentication methods. Secrets engines are responsible for storing and generating secrets. For our CI/CD use case, the key value, KV, secrets engine is perfect for storing static secrets like API keys or database credentials. It's like a secure, versioned, key value store. On the other hand, authentication methods define how clients, like our CI/CD pipeline, authenticate with Vault. For cloud-native CI/CD environments, OpenID Connect, or OIDC, is the gold standard. OIDC allows your CI/CD provider, such as GitHub Actions, to authenticate to Vault without needing static credentials. Instead, it leverages the CI/CD provider's inherent identity, providing a secure, credential-less authentication flow. This separation of concerns ensures that secrets are stored securely and access is granted only to authenticated and authorized entities. Now, let's talk about the specific CI/CD pipeline we'll be demonstrating today: GitHub Actions. GitHub Actions is an incredibly popular and flexible CI/CD platform built directly into GitHub repositories. It allows you to automate software development workflows, from building and testing code to deploying applications. Workflows are defined in YAML files within your repository, specifying a series of jobs and steps that run on hosted or self-hosted runners. Each job runs in a clean environment, and each step within a job executes a specific task, such as checking out code, setting up environments, or running commands. It's the perfect environment to illustrate how securely integrating Vault can transform your secret management strategy, making it robust and scalable, right within your existing development ecosystem. So, how does a GitHub Actions workflow actually talk to Vault without hard-coded credentials? This is where the magic of OIDC authentication truly shines. When a GitHub Actions workflow runs, it automatically requests a JSON Web Token, or JWT, from GitHub's OIDC provider. This JWT acts as a verifiable identity for the running workflow. Our GitHub Actions workflow then uses the official HashiCorp/Vault action, a powerful community action, to present this JWT to Vault's OIDC authentication endpoint. Vault, having been configured to trust GitHub's OIDC provider, validates the JWT's signature and claims. This handshake ensures that only legitimate GitHub Actions workflows from your specified repository can attempt to authenticate, eliminating the need to embed long-lived tokens or keys directly in your pipeline code. It's a truly credential-less and highly secure way for your pipeline to identify itself to Vault. Once Vault has authenticated the GitHub Actions workflow using OIDC, the next critical step is policy enforcement. Vault doesn't just grant blanket access. Instead, it applies granular policies to ensure the principle of least privilege. In our demonstration, we configure a Vault policy, perhaps named MyApp policy, that grants only read access to a specific path within our KV secrets engine, for instance, kv v2/data/myapp/db creds. We then create an OIDC role, like GitHub Actions, that binds specific GitHub action identity attributes, such as the repository name or branch, bound_claims, and a JWT_audience value, to this MyApp policy. This means that even if a workflow successfully authenticates, it will only receive a temporary Vault token with the exact permissions defined by MyApp policy, strictly limiting its access to just the secrets it needs for that specific job and nothing more. This is a fundamental pillar of robust security architecture. With a validated token in hand, the Vault action proceeds to the secret retrieval phase. Using the temporary Vault token it just acquired, the action sends requests to the KV secrets engine to fetch the specified secrets, in our case, the username and password for DB creds. The Vault action is designed to be smart about this. You simply list the secrets you need and their paths. Crucially, by setting export_secrets, true in the Vault action configuration, these retrieved secrets are then securely injected as environment variables directly into the GitHub Actions job's runtime environment. This means that subsequent steps in your workflow, like running your application build or deployment script, can access these sensitive values as regular environment variables without ever needing to interact with Vault themselves. The Vault action handles all the complexity of authentication and retrieval, making the secrets readily available and completely isolated from your source code. After retrieval and injection, the application execution phase begins. Our simple Python application, app/main.py, demonstrates how an application consumes these secrets. It doesn't know or care that these secrets came from Vault. It simply reads db_username and db_password from its environment variables, just as it would any other configuration. This is a powerful pattern. Your application code remains clean, agnostic to the secret management solution, and focused on its core logic. Furthermore, for sensitive values like passwords, it's a critical security best practice to mask them in any output or logs. Our example main.py explicitly masks the password when printing, ensuring that sensitive data is never accidentally exposed in plain text within your CI/CD logs. This layered approach to security, from Vault secure storage to careful application consumption, forms a strong defense against data breaches. Now, let's briefly look at how you'd set up such an environment, conceptually. We've provided a complete example in the repository. First, a docker compose.yml file allows you to quickly spin up a local HashiCorp Vault server in developer mode. This makes it easy to get Vault running for testing and demonstration purposes without a complex production setup. Next, a script/vault_setup.sh script automates the configuration of this local Vault instance. This script handles enabling the KV secrets engine, writing a sample secret, enabling the OIDC authentication method, configuring it to trust GitHub Actions, creating the necessary Vault policy to grant read access to our secret, and finally, defining the OIDC role that binds GitHub action identities to this policy. This scripted approach ensures consistency and repeatability, demonstrating the full lifecycle from setup to secret retrieval in a reproducible manner. With Vault configured and our application ready, the .github/workflows/ci.yml file is where all the pieces come together within your GitHub repository. This workflow is triggered on a push to the main branch. The crucial part is the login to Vault and retrieve secret step, which leverages the HashiCorp/Vault action. This action is configured with the Vault server URL, which would be your public Vault address in a real scenario, specifies OIDC as the authentication method, and points to the GitHub Actions role we configured in Vault. Importantly, it also includes the JWT_audience, which must match the bound_audiences in your Vault OIDC role, ensuring Vault only trusts tokens issued for the correct audience. Finally, it lists the specific KV v2 secrets to retrieve. Once these secrets are retrieved and exported, the run application step simply executes our app/main.py script, proving that the secrets were successfully injected as environment variables. This seamless integration showcases how your CI/CD pipeline can dynamically fetch credentials, maintaining robust security practices throughout the entire development lifecycle. So, what are the key takeaways from this demonstration? Firstly, and most importantly, no hard-coded secrets. Vault eliminates